The purpose of this video is to highlight how do you find the area of quadrilaterals. And one of the important pieces that this uses is the knowledge of, well, we've already dealt with triangles. We've already said that any other polygon can just be made up of triangles. So in order to find the area of these other guys, or a description of that area, we just need to know what sort of triangles will actually work. Okay. So we start off with several different shapes. These quadrilaterals are all parallelograms, meaning that they have two sets of parallel sides. They have a variety of pieces, like the square, which of course has all four sides congruent, the rhombus, which has the same issue, a rectangle, which just has 490 degrees, 4 right angles, and then just the generic parallelogram. So this pretty much covers all of the quadrilaterals that have two sets of parallel sides. So we first begin by taking a look, and I'm going to shift this over, and saying we can make any one of these into some sort of combination of triangles in order to figure out how to find their area. Recall the area just of a generic triangle, okay, so of just a triangle is where the height is given and the base is given. The area is 1/2 the base times the height. Okay, where the only requirement is that those two, the base and the height, are perpendicular, where this is the sign for perpendicular. Okay, so we first take a look at the square. Okay, chances are you already know what the area of a square is. Okay, but we also know that we can create a diagonal between the two vertices that create two congruent triangles. Okay? What is the area of either one of those triangles? Well, it's again 1/2 the base times the height. Okay, just as before. Well, for the square, the side length S, okay, is both the base and the height. So we have two triangles, both of which have an area 1/2 the base times the height, or in other words, S squared, the side length squared. Okay? So clearly for a square it's very easy. Not much different for a rectangle. We're actually going to do that one next. We again just draw a line connecting the two vertices, and we again have two congruent triangles. We know that by side, 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 or side, angle, side. Any of the versions of congruency that we've done before are actually valid here because we know everything about these particular triangles. Okay? Whereas before, for the square, the side lengths were S. These ones we're going to actually have to mark as a base and a height. Okay? But again, it follows the same rule. You have two of these triangles, each of which has 1/2 a base times a height, where for the other part of the triangle, it's just base and height over here. It does not matter which side the base is on. It can be at the top side of the triangle, such as here, just so long as the base and the height themselves are mutually perpendicular. Okay? The result of this, of course, just gives us the familiar equation for a rectangle, that the area is the base times the height. Okay? And the area of the square is S squared. Okay? We're now going to jump over a little bit and take a look at this parallelogram. Okay? Where our requirement is that we have a base and a height, and that the height be perpendicular. But our other edge is certainly not perpendicular to our base. So how do we do that? Well, just like when we were doing triangles, if we didn't have a right triangle, we just constructed an altitude, which was perpendicular, and we're not going to do a formal perpendicular line here, but we're just going to draw this line here, which is basically the equivalent of an altitude. Okay? Because we can, we're also going to draw that altitude over here, which will become clear in a second. So what do we really have? Okay? We have a base, which is the total length, and a height, which is given here. Okay? But what is this shape really? If we were to take this triangle and just shift it on over to this piece, Notice that this area actually matches this one. We now have the base being this distance here, with the height still being this guy. We now have the formula equation for a rectangle. Okay? It comes from the exact same spot. Okay? So the area for a parallelogram is again equal to the base times the height. Okay? Notice that there's a pattern here. All three of these are all base times the height. Okay? So now we need to be a bit more clever. How are we going to deal with the rhombus? Okay? I mean, we can't just take one side times another. It certainly isn't s squared. Okay? But we follow the same prescription that we did for the generic parallelogram. We just take one side, we call it the base, and then we draw an altitude. Okay? Now, since a rhombus is itself a parallelogram, it must follow the same rule as before. So we're expecting this to also be the base times the height. If we call this entire distance the base, and then the dotted line the height, we notice we can again, if we were to take this triangle right here, okay, I'm going to shift that up. If we were to take this triangle right here and shift it over to this spot, okay, it would actually complete it as if it were a rectangle of base this same distance. Okay, just because this was shifted over to the other side doesn't change the overall length. Okay, and a particular height. So again, we have the area is equal to the base times the height. So we have a generic rule then for all parallelograms. Anything with two sets of parallel sides will have an area given by the base times the height. Now, what's different when we move to one set of parallel sides? Say, for example, the trapezoids. Okay? We have two different types of trapezoids that we really consider. One is the isosceles, where the two opposite edges that are not parallel are congruent. And then we have just another generic trapezoid. Okay? It could be facing a right angle at this point, but it doesn't have to. Okay? It generally, the area equation for him will generally work. But we can again kind of view what's going on with triangles in order to establish, okay, how do we find the area of these guys? So, for example, we'll label this as having base 1 and base 2. Okay? So, what we can do is, again, draw the altitudes, because remember, if we're going to do things similar to triangles, we're going to want to have the altitudes in there. Okay? And this is H, and this is H. Okay. We can again kind of apply that whole transformation business of taking this triangle and slapping it on the other side. We know that it's going to, because it's a congruent pair with the other triangle, just make a nice little piece here. Okay. But what is that total length? Okay. It's not B1 because there's extra bit. It's not B2 because it's missing this guy. How much is it actually? Well, it's actually going to be halfway between. Okay? When we do this, the amount that you lose here is the amount that is gained by B1. Okay? So it's the midway point of B1 plus B2 is basically the equivalent base of this figure. Okay? When we do this, though, it's half of that. Sorry, this is the equivalent base. It's somewhere between those two. In fact, it's actually the midway point between those two. Okay, so this is the equivalent base of this figure times the height. Notice this is very, very similar to what we had before. You have an equivalent base times your height. Okay, for the area of a trapezoidal or an isosceles trapezoid. Okay. Well, now we look and we say, okay, this one here is going to be a bit different. We don't have a congruent pair triangle to just throw on the other side. We're going to, again, draw those altitudes. The good thing is that those altitudes have to be the same height, because the two lines that they join are both parallel. But here we're going to use a slightly different notation. We're going to again call this B1. Overall this is B2, but we're going to call this A, B, and C, where the total length is just B2. So if I add all three of those segments up, I will just get B2. My height, of course, is given here. Okay? So the question is, how do we find the area of this piece? Well, we know we have the area of the rectangle. The rectangle piece is just B1H. And then we have two triangles of which we can find the area of. They are 1/2, I should label this as B1, I suppose, 1/2 CH plus 1/2 AH. Well, this could be kind of cumbersome, so let's see if we can tease out an easier way to show this relationship. Okay. H is a common factor in here, okay? But B1 can really be separated into two pieces. 1/2 of it plus another half of it. So when you add these two pieces together, of course, you just get the original back again. Now, let's take a look at this. If I can combine these terms and in fact factor out the important pieces, I have 1/2 B1 plus C plus A all times H, and then of course the original one, 1/2 B1H. Okay. But what does this become? Okay. This, of course, was just the original sum we had here. So we have 1/2 B1H plus 1/2 B2H. Okay. But then we notice, well, we can again pull this factoring business again. We have B1 plus B2 over 2, 1/2 of B1 plus B2 times H. Okay. But what's special about that? We automatically know that this is the same as when we had the isosceles triangle or isosceles trapezoid. So this means that we have identical pieces for both the trapezoids. Okay? When one trapezoid, his equation is just given quite simply as this, the other trapezoid's equation is given here as well. Okay? And they are identical. So anytime you have a trapezoid, this is a valid equation to use regardless of how it looks.